Welcome back to the lecture series on GPU architectures and programming. So, if you remember in the last lecture, we explained in detail the idea of thread level coarsening, and we are looking into some examples of block level coarsening. So, just a small point we like to make before getting into further with the block level coarsening example. So, if you remember in the thread level coarsening, we talked about what is the minimum stride length, and we said that it should be greater than the warp size. So, just to clarify a bit that of course, we understand that the basic idea is that it should ensure whatever was the original global memory transactions and coalescing behaviors, they should work fine. Just to clarify why we will clarify further on this, consider this example that you have a warp of threads. So, this is one warp, and it was originally accessing consecutive data elements. Now, you have coarsened them, let us say by some factor of 2, and the stride length is not greater than the warp size. The stride length is, let us say, 4. So, if it was greater than the warp size, then the thread should access the original consecutive data elements followed by. So, this is the original consecutive 32 data elements in one global memory transaction, and then since if the stride is 32, then it will access the next 32 consecutive data elements in a next transaction. That is perfect coalescing activity. Now, if the warp size, the stride is, let us say, 4, then in the first transaction it is bringing the data like this, the original one global transaction. But what more does it want? Each thread now wants the data sitting at an offset of 4, right. So, in the next transaction it is going to bring the same data starting with an offset of 4 up to this much, right. So, in the next global memory transaction is going to bring starting it should the next global memory transaction. So, in the original behavior, this was the first transaction, this was the second transaction, but now this would be the first transaction and the second transaction. Let us say the offset is this, offset is this. So, second transaction would be something like this. Now, see, there is lot of commonality in the data points. So, we are actually losing out on the coalescing behavior in the global scale, looking at all the threads in the kernel, because there is lot of reuse happening. We are not able to cover more number of global memory elements through a perfect coalescing behavior that was achieved in the original. Now, this can be easily alleviated if we increase the stride from 4 to 32, which is the warp size, because then there will be no extra redundant global memory transaction or bringing data, and perfect coalescing would be achieved. So, this is one point we wanted to clarify about thread level coarsening, and then let us move to the example on block level coarsening we are talking about. So, the first idea about block level coarsening was that since the threads will be picking up activities from blocks sitting at a specific stride length, considering coarsening factor of 2, we are going to compute 2 global thread IDs. In this case, it is I0 and I1, and they are both corresponding to thread IDs which are sitting at the same offset value of TIDX. So, we compute only one local thread ID, and we use that single local thread ID to get multiple global thread IDs from different blocks. Since we are using a coarsening factor of 2, so you multiply the block IDX by 2 wherever it occurs, and since we are using a stride of 1, you should have this 2 block IDX plus 1 for taking the thread from the adjacent blocks, right. Adjacent blocks, threads from adjacent blocks and threads with the exact same local offset. So, now once I have picked up the threads, the rest of the thing is quite same. You are going to have to bring the data from the global memory, but then there is something important. Earlier in the previous example of thread level coarsening, you are coarsening the block, right. You are coarsening the threads by using activity inside the block. So, effectively the requirement of each block was remaining same, right. The compute requirement of each block was remaining same. the threads inside the block were getting thickened, and the number of threads inside the block were decreasing by the coarsening factor. But now you are creating a block with more amount of activity with respect to the original block, and you are not reducing the number of threads, right? So when we talk of a reduction kernel, or for that matter any kernel, the resource requirements at the block level is increasing, right? So again I will just like to highlight, in the original thread level coarsening, the resource requirement at the block level was kept constant. The thread level requirements were increasing, so the SM could accommodate more number of thread blocks, right? In case the part thread level resource requirements were not too high. But here what is happening is the thread level activity is increasing, but the threads per block is not decreasing, it's constant. So effectively the block level activity is increasing. For example, since I have a coarsening factor of 2 for a reduction kernel, now each thread inside the block is bringing in effectively double the amount of data, and so we will need 2 shared memory locations. So we are just allocating 2 shared memories, S data 0, S data 1, each of size equal to the new block size, right? And the block size of course is the same, because we don't decrease the number of threads per block. So now for thread ID, the first thread ID, I am just using the global thread ID I0 to load data in S data 0. I am using the global thread ID I1 to load data in the other shared memory, which is S data 1. Now observe one thing, when I am using I0 or I1, I am loading data from adjacent blocks. I am loading the data into 2 shared memories. Since I am loading the data from adjacent blocks with the same offset, I am loading the data in the different shared memories in the same offset. So just to highlight, consider these adjacent blocks. So these are adjacent blocks, right? Thread block 1, thread block 2. Let us say I am loading data from here, right? The offset is TID. I am loading data from here. Here also the offset is same, right? Now this data will go to shared memory S data 0. This data will go to shared memory S data 1, and the location in which the data would go will also have the identical offset, right? Because these shared memory sizes are same as the thread block sizes, right? So with one thread I am loading data from 2 adjacent thread blocks into 2 shared memories, 2 different shared memory segments at identical locations. Okay. Now once this is done, you perform the reduction in each of these shared memories in parallel, right? So all the threads would parallelly load data into the shared memories, then all the threads would go into doing the reduction. So it will do, all the threads will do reduce step here as well as here, then again in another reduce step parallelly in both the S datas, and like that, right? So earlier we were reducing in a per block basis, and when we did thread level coarsening, each thread was reducing more number of locations. Now we are reducing across blocks, and each thread is doing 2 reduction steps in adjacent blocks by bringing the data in the corresponding shared memory locations. And once all the reduced steps of course keep on synchronizing for each stride value, where the stride, by stride I mean the stride of reduction in the original for loop, right? And when this is done, then of course you copy back the data from the shared memory locations. So if you just do a small recap of reduction, so these were the different optimizations that were going on, right? So for reduction 1, your optimization was that you were using so there were a lot of problems in that basic reduction kernel. So there was interleaved addressing, but you are not really using consecutive threads. So so first of all, that was a problem, because the warps will contain threads which are not really active. So the warps will also have lot of underutilized occupancy of threads. That was first problem. And then there was the modular arithmetic, which was also overhead. And then there was divergent branches, right? Because some of the warps were not, some threads in the warps would actually have no work, right? And then you, in the reduced reduction 2 step, you used interleaved addressing, but now you have to actually worked with contiguous threads, and that led to balanced warps because the threads will not diverge, but still you had the problem of bank conflicts. And then in reduction 3, so this is again I am doing a small recap of the reduction steps because this is relevant here. So in the reduction 3 step, what you did was you actually performed sequential addressing, and you actually removed the shared memory bank conflicts. Then in the 4th step of reduction, you halved the number of threads and delegated some activity to the threads in terms of global loads. So each thread was practically coarsened to do global loads. So this is the step from where you start increasing the per thread activity. So this is like some example of coarsening inside the reduction kernels itself. So you use actually n by 2 number of threads. Then in reduction 5, you unroll the last warp, and you were able to remove intra-warp synchronization barriers for the last warp and all that. And if you remember, in reduction 6, you performed a template parameter based complete unrolling of the kernel based on whatever is the block size. You will be generating code where there was effectively no loop, and it was a completely unrolled version of the kernel, right? So all the loop overheads were removed. And then in reduction 7, you had multiple elements per thread and you launched very small constant number of thread blocks. So that was also somewhere you have increased the per thread activity significantly, and it was requiring very few synchronization barriers, right? So this the point we are trying to make here, first of all, these are the reduction steps we are referencing. Some of this we have discussed up to some level of detail, and you can easily find the further detail of all these reduction steps in the NVIDIA example of reduction kernel optimization, which is easily available online and which has been referenced in our earlier lectures. So the point we are trying to make here is, with each higher step of reduction, we are increasing the per thread activity significantly and actually removing lot of redundancy and unnecessary barriers and unnecessary loop overheads and things like that. So the point here is that if we are actually applying thread coarsening into these different variants of these reductions, we see that how things perform, right? So here we do an analysis of how coarsening affects the execution time for each of these reduction kernels. Okay, so in this plot we provide the examples of these reduction kernels. So here what we have is these different reduction kernels and their overheads in terms their peak throughputs and how the throughputs keep on changing with the different coarsening factors. So this is the plot for reduction 7, and the other plots are for the reduction kernel. This is for the reduction kernel 1, then the 2, 3, 4, 5, 6, and this is the 7th kernel. So they are in this order. Sorry, the legend in the figure is missing here. So I hope it's, I mean, you can see that with more amount of optimization, the initial speed up, as you can see in terms of throughput, there is a it keeps on increasing, right? So this is reduction 1, this is reduction 2, 3, 4, 5, 6, and 7, right? Now observe firstly that, and so here we are using a Kepler architecture based system, Tesla K40 card in our system, and we are applying a thread level course. We are actually using two different kinds of optimizations. One optimization is the coarsening optimization, we are applying thread level coarsening and we are applying block level coarsening. So, the first important characteristics we see here is that the optimal coarsening factor for all of the first 6 reduction kernels appears to be the coarsening factor of 4, both for thread level and block level coarsening. This is for our system and for this specific example of reduction. And for reduction kernel 7, we see that coarsening does not really help. It first remains constant or increases a bit in terms of the peak throughput, right. So, that by the way, that is the index. It is telling me that how many that what is the throughput of the kernel, and with coarsening is going to increase. But however, for reduction 7 we see that it is gradually decreasing, right. By the way, we would like to say that this is a plot we are we are actually reproducing from this reference, which is actually highlighted here at the end. So, this is from this paper, and these results actually are given from this paper, right. We also have these kernel versions, but these specific plots that we have given, they have been directly taken from this paper. You can also try them. We have tried these programs, and it's very easy to reproduce this behavior in your own system. Of course, the coarsening factors may be different, but this is an example, and the plots which you have directly taken from this reference here, right. So, what they are trying to show is how for the reduction kernels the activities keep on changing, and as I was saying that for reduction 7 you see that there is no real effect of coarsening, but for all the others it seems that coarsening by a factor of 4 is actually providing you the peak throughput. So, this is the observation first brought out by the authors of this paper, which appeared recently. Now, if we try to analyze, we thought that this would be a very nice example for this specific part course material on thread coarsening, because it really brings out the effect that coarsening has on in terms of the occupancy of the architecture. Okay. First of all, let us understand why for reduction 7 there is no significant speed up. Now, if you remember what was happening in reduction 7, in reduction 6, so first of all we started coarsening of threads in terms of increasing, not really coarsening of threads, but actually increasing per thread activity from reduction 4, right. So, I would not say we coarsened threads, but we just simply delegated some activities for the threads. It was not in the semantics of coarsening, so we will not say that. For if you see from reduce 4, we delegated some activity to the threads, right. It was in terms of performing more number of global loads, right. But then it was only normal per thread activity. So, we should not say it is a coarsening, but just increasing the per thread activity, but that also increases the amount of resources the threads are going to consume in terms of memory traffic here, in terms of storage in the registers here. Then in reduce 5, it was simple, you just unrolled the last var for reduction. In reduce 6, we completely unrolled. So, these are more or less 5 and 6 are optimizations where you remove the loop overheads and you remove the synchronization overheads, specifically in reduce 5, right. Reduce 6 completely removes the loop overheads. But what happens in reduce 7? In reduce 7, the idea of making each thread work some more is being generalized. So, instead of making each thread bring some only 2 data points, we can make each thread bring multiple more number of data points and make them do the local additions on global memory data. So, each thread is given more amount of sequential activity in general. So, let us say they are adding up, they are bringing n data elements from the global memory, adding them up, and then starts the usual reduction behavior, right. So, reduce 7 actually is a good optimization where you can select the amount of sequential addition each of the threads are going to do, such that overall we have the perfect occupancy in terms of the reduction kernel, right. So, as you can see, with each reduction step we are doing an optimization. At some point we have reached all the possible optimizations. Now, what you are trying to do is you are trying to increase the per thread activity so that you get the perfect amount of occupancy, right. So, the perfect amount of occupancy can be achieved if whatever is the total number of threads you are able to schedule in your GPU's SM, you you make all the threads, that this peak number of threads use all the SM resources maximally, right? So then that's your perfect notion of occupancy, and which it seems that with a suitable amount of, with suitable choice of per thread activity in terms of number of sequential loads, I can tune this value and make reduce 7 achieve that perfect occupancy. Now once we do that, I hope it's clear to us that once we are able to tune that perfect occupancy just by increasing the sequential activity per thread with respect to reduce 7, further coarsening is not really going to help, because whatever is the peak parallelism to be explored is already done with reduce 7, right? So that explains this figure, which has been reported by this publication reference. And but let's now try and analyze in our terms that why really these authors were able to get a peak throughput in the Kepler architecture for the other reduction kernels at a coarsening factor of 4. So if you look into the target architecture and the test data set for this work, so this is some analysis we are doing, and maybe this is a very good example where we are really talking about optimization in terms of not only algorithmic optimization but also the optimization with respect to the architectural parameters that are there. So here the device under test is a NVIDIA GeForce GTX Titan Black GPU for this specific work by the authors, and their GPU is of Kepler architecture. Number of SMs is 15. The SMs allow maximum active threads per SM as 2048, maximum thread blocks per SM as 16. So observe, these are very important parameters. So maximum number of active threads allowed is 2048, maximum thread blocks allowed is 16. The number of registers in the register file inside the SM is 64K, that's the size, file size, and then shared memory is 48 KB, and the maximum shared memory provided allowable per block is also the same. So right, and the test data size, the data set size for which the reduction has been performed is of 512 megabytes, right? The data type is single precision floating point in this for the reduction kernel, so that's 4 byte. So if we consider the block size for the original uncoarsened code, it has been taken as 512, and so since the block, so I have 512 data points and each of them are floating point type, so the shared memory requirement for each block is also 2048 bytes, right? So this is important. In the uncoarsened version, the shared memory requirement per block is 2048. Total amount of shared memory available in the SM is 48 kilobytes, right? So let's figure out what is a good coarsening factor here. Let X be the coarsening factor, right? So what is the block size? We are saying that effectively the block size, if I am doing thread level coarsening, so I am going to reduce the threads per block. So that would be reduced by original block size of 512. So this was the original block size 512. That would get reduced by X, right? 512 by X is the reduced block size. With this, what would be the number of active blocks per SM? So as you can see that you have maximum active threads per SM is 2048, right? Now there is a maximum allowed limit on active threads per SM. So now it's going to be active blocks per SM would be original total 2048 threads, and threads per block is 512 by X. So that would give me 2048 divided by this, so that gives me 4X, right? Of course, the other limiting factor is maximum thread blocks per SM, which is 16. We are just hoping that we will be reaching the threshold by this limiting factor, otherwise you have to consider the other limiting factor also, right? So for the thread level coarsening, the shared memory requirement per block remains same, as we know, because we are coarsening the threads and reducing the threads per block simultaneously, so per block remains same. So what is that requirement? So shared memory requirement per block is 512 times 4, which is 2048 byte, as we have computed earlier already. And in that case, since we know that active blocks per SM would be 4X, so what is the shared memory requirement overall per SM? So that is 4X times 2048 byte, and of course the maximum allowable shared memory in the SM is 48 KB. So here we have an equation. So we have 48 times 1024, and that should be equal to this 4x times 2048 byte, right. So 48 KB, that's multiplied by 1024. Solve it, you get x equal to 6. Now if we put the nearest value in terms of, I mean here if you just get the lower value in terms of the powers of 2, so you get it as 4. Since you have it, the course you can so since it's 6, so you have to go to the next lower power of 2. Will be coarsening always in powers of 2 like that, and that would give you the 4 here, right. So with that we see that if we choose 4, we get the coarsening factor as 4 here out of this calculation, that with this value of 4 we are making a use of shared memory such that we have the maximum possible occupancy. If we go beyond this, then what would happen is that with further coarsen threads, the number of blocks that you can the number of threads that you can really schedule, they will go to be less than the number of active threads per SM, because they will keep on requiring more amount of shared memory, right. So this is a possible calculation that you can do for thread level coarsening. But of course you can but here in this calculation we are just using the limiting factor, which is the number of active blocks per SM, where the limiting factor is taken as 2048. You can just check whether the other limiting factor, which is threads per block per SM, is also limiting this value of x. Is just a take home. You can just check it and see whether with that if I consider that constant, I hope you are understanding that here we are considering the constant of the maximum number of active threads and computing using that okay, in that case what can be the number of active blocks, right. But we also know that with this the maximum number of thread blocks is 16. So here with x equal to 4 I get this as 16, right. So that anyway would mean that I cannot go beyond this, because with a higher factor what would happen is it may happen that you can also hit this limiting factor. So in general you have to take care of both. You can do a calculation and figure out whether if you just start with this as the limiting factor, what value do you get, and whether it hits the other barrier in terms of the other limiting factor, which is this, right. They are kind of related. So you can just replicate a similar analysis for block level coarsening. So choose x as a coarsening factor. Block size is known for the original uncoarsened version of the kernel. Active blocks are for SM would be in that case 4 like us like the original. And so shared memory requirement per block you can just, so here will be what it will increase by the x value, right. Shared memory requirement per block, whatever was original, it multiplies by the x value, and then shared memory requirement per SM would be multiplied by the requirement per block multiplied by the number of blocks, so you multiply by 4. So then you can just have a equation where you have this shared memory requirement per SM equal to the maximum allowed shared memory, which is 48 KB. So 48 multiplied by 1024, and you get the similar calculations again, right. So these are the possible ways in which you can also empirically derive limit on the coarsening factor. But of course there are other issues in the architecture in terms of nonlinear relationships between the different factors like interference and other issues. We are not going to that detail. We are just trying to provide a handle here, like how you can analyze that, why possibly you are reaching this kind of a peak performance with this coarsening factor here. So there are several other effects of detrimental effects of thread coarsening, which also gets exemplified with this picture. As you can see that the peak throughput we are getting with the coarsening factor 4 both for thread and block level, but then the peak throughput reduces for increased coarsening factors of 8 and 16. Now we have discussed this that with higher amount of coarsening I can have reduced occupancy, right. And the reason being the kernel's resource consumption increases, right. Per thread resource consumption in terms of registers and shared memory increases, and that is resulting in the reduced occupancy. The other important thing is this also creates an increase in the pressure on the kernel. So this is an important parameter which is cache pressure, right. So a few words on cache pressure. So if you are overworking the memory cache with too many or wasteful memory accesses, then it's a bad thing, and that's the effect on the cache is modeled by this term cache pressure, right? Now it may happen that you are reusing a cache line time and again by a single thread, which is not a good idea for a GPU. And that can create issues. So when I am doing cache line reuse for data, that means one thread is accessing the same cache line multiple times, it's considered bad for the GPU, because in the GPU I would like to have consecutive thread IDs inside a warp accessing sequential data elements, and that would mean a single warp makes a single cache line access and brings in the data, rather than one thread bringing data multiple times in different iterations of a loop or similar kind of activities. So whenever there is cache line reuse, that's a bad thing in a GPU, unlike a conventional serial architecture where it's considered a good thing, right? So if you have a GPU kernel where a thread is accessing a cache line multiple times, let us say you have a for loop using which the thread is accessing consecutive data elements, then that's a bad thing. Ideally you should not be writing the code like that, but if the program's nature is such that the thread is accessing consecutive locations, then in terms of warps is going to access the cache line multiple times by the same thread, which is good in the sequential serial architecture but not in the GPU. Now consider that you are coarsening this kind of a program. So then this thread will be performing its own execution of a for loop where it's making multiple accesses of a cache line, and it will also be doing the activity of another thread in the original kernel, and for that also it will be sequentially accessing the elements inside the same cache line. So if the original kernel has got lot of instances of part thread cache line reuse, in the coarsened kernel there will be further iterations. So just if I am trying to take a picture here, that suppose you have a for loop through which one thread you have a behavior such that one thread ID is accessing the same cache line for consecutive memory locations, right? So so there is one load instruction here, and it's increasing with the index I, and the for loop is iterating over I, and one thread is looking into the same cache line time and again, and it's making a cache line reuse. For this kind of a code, when I do the coarsening, so then the thread will do this behavior for multiple cache lines, right? Because it will also replicate some other thread's activity and again do cache line reuse here. Well, it was originally doing cache line reuse only in one place. So this is a bad thing. In this, first of all, this is a bad programming behavior for a GPU. Ideally, this sequential accesses should have been delegated to sequential threads. But if that the nature of the algorithm, as I am saying, so then you are increasing cache line reuse by a coarsening factor, which is significantly increasing the cache pressure, and due to this, the overall kernel's throughput will decrease, right? So that's the impact of cache pressure on a program, and coarsening will hamper it further, right? So in general, I can say that if I do a coarsening, in the worst case, the same number of active threads per SM will be executing as in the original kernel, but now each thread will of course be doing more work, and due to each thread doing more work, if the work is to load the cache line multiple times, then the number of cache lines accessed will also scale with the coarsening factor, just as we are saying, and with higher amount of coarsening factors, we will have more higher cache line reuse, and that will effectively bog down the SM and decrease the occupancy in that way, and this will significantly outweigh the benefit of performing any kind of coarsening whatsoever, right? Now let's take another example of the matrix transpose kernel, which we know as it's a quite difficult kernel, and there are a lot of optimizations which we have already discussed. Now let's have a relook into this. from the point of view of coarsening. So, in the single matrix transpose kernel, each thread will read a single element from the source array and write to the target array. Let us consider the situation where we are doing coalesced reads and uncoalesced column wise writes, right. So, the cache line is read in a coalesced fashion by threads in the single warp because we are doing coalesced read. So, there is no much of cache line reuse in terms of read, but when the writes are going to happen, they are uncoalesced, right. So, writing to the different cache lines is happening in an uncoalesced way for multiple different warps, right. So, the data cached for read first of all is not going to be accessed again. So, that is the thing, that when you are reading from here, you are reading in one shot, right. So, you are reading in one shot. After the data has been read, this cache line is not going to be accessed, but that does not mean immediately after the read has happened, the cache line will be evicted. Why? Because the read is performed quickly, but then the write is going to happen column wise in an uncoalesced way from multiple warps. So, the write is going to happen in multiple cycles, right. So, for the same warp, so let us say this is the warp which has performed the read. This warp is going to load the data here in the write in multiple cache transactions, right. So, there will be multiple cache transactions happening. So, at any point of time we should be saying that, well, there are a lot of write instructions in flight. Since there are a lot of write instructions in flight and the average latency of the cache write is very high, and that effectively increases the amount of time for which I am unable to evict the data from a cache line. I hope this is clear. As long as I am not able to read as well as write back the data column wise, I cannot evict data from the cache, right. Now, since the writes are getting serialized in this case, I am unable to perform, I am unable to actually evict the data. So, that creates significant delay and decreases the throughput. So, as the writes are coming from the different warps, the cache line will not be evicted until the data is written by all the warps responsible for the writing. So, the read is coalesced, write is uncoalesced, write takes multiple cache cycles. So, I cannot evict the data from the cache line even immediately after the read happens, right. So, for a coarsening factor of 2, I will have twice as many instructions which may be in flight at any time. So, I hope you are understanding that if we consider this transpose operation, already there was this difficulty with the write and there was this issue with the cache, right. Now, if I increase the coarsening factor, earlier whatever was the number of instructions which were in flight at any time, that would increase by the factor itself, right. So, the average time for completing the writes to the cache are going to increase. It was already high, the average time was already high, the average time for the cache line eviction was high, and since the write time will increase further due to the coarsening increases the per thread activity, the coarsening will increase the amount of data to be written to the column. So, we will just go back again. If we coarsen, what happens? Now, we will be reading more amount of data in the coalesced read. So, again we will be writing more amount of data in the coalesced write by inside the single thread. I am not having the advantage of having multiple threads to do the writes, right. So, the amount of sequential column wise access here for the data will increase. So, that would further increase the cache line reuse here, that would further increase the amount of time for which I cannot evict the data from the cache, right. So, this also will create a problem here. And so, just as an example, this was our uncoarsened version of the transpose kernel we have seen earlier. So, you just you compute the index in row wise input and you write column wise, right. And for this kind of a non-optimized matrix transpose kernel, the effect of coarsening is severely bad, right. So, it primarily depends on how threads are scheduled on the SMN memory system. Of course, that is a dependency, and if we coarsen by a factor of 2, as we are saying, there will be 2 read write statements. So, twice as many read and write instructions are required here, twice as many, of course, because I'm increasing the path thread activity by 2, and as we increasing the coarsening factor, the number of cache line access will increase, right, because now each thread will access more, and now that would effectively increase the cache pressure, and the average time taken to complete the write to the cache line increases, as we have discussed. Since the time taken to complete the write increases, it also increases the overall latency, and it decreases the performance in terms of, as we have seen from the picture, that after 4, I mean for the reduction kernel there was a decrease, but for transpose, doing any kind of coarsening is going to be difficult, especially for this transpose kernel where we have this kind of a column wise write and row wise reads, right. So this is the simple example here. This is a picture again taken from the reference paper we are talking about, that for this kind of a matrix transpose, by the way, this is the unoptimized matrix transpose that we discussed earlier in our lectures on matrix transpose. As you can see, any kind of coarsening is actually creating the cache pressure and cache line reuse issue, and increasing the latency of the writes, and due to that any kind of coarsening is leading to a hamper in the leading to complete hampering of the speed up, right. So with this we would like to end our discussions on the different on thread coarsening, its good and bad ways. I hope we have performed a good architectural level analysis specifically for these examples. So you can really think more in these terms for other examples and their other example algorithms and their coarsenings. And here are some of the references, important references which we used for this lecture material. This is a reference on kernel fusion which we extensively used. Then the second reference on kernel fusion, these are all, some of them are quite recent papers actually, and the thread coarsening part was almost entirely taken from this predictable thread coarsening paper which appeared very recently. And of course this is another paper on optimizations with respect to thread coarsening, right. So with this we will be ending this long lecture, and thank you for your attention.